The first case is, special case number 1 is when we are having 0 at the first column. While calculating the table, look at the table here. He's putting example. This is the example. This is the closed loop transfer function. That means this is the characteristic equation. When he build it, he will find that s to the power 5 is 1, s to the power 2 is 2, s to the power 3, and so on. So he distribute 1, 2, 3, 6, 5, 3. Finish. Now I will start building the table. I will start continuing the table. If I want to get this item, the item here, how to calculate it? It's 6 into 1, of course minus at the beginning. It's minus, to calculate this item, it's minus 6 into 1 minus 3 into 2, all divided by 2. So when you calculate it, you are going to find that 6 minus 6 is equal to 0. So it ends up with 0 here. It ends up with 0. And that's the problem. If I keep the 0, you are going to get the rest of the table zeros or infinities. You cannot continue with the table. And remember, I don't need the value here. In this kind of calculation, I don't need the value. I need only the sign. For that, he's saying, let us replace this 0 by certain value. That value is considered as a very small value. So it's going to be epsilon. So epsilon is nothing but any small value. A value which is smaller than the values given here in the column. These values. For a matter of simplicity, assume that this epsilon is equal to 0.001, for example, and keep it. So we will keep it as an epsilon. Or actually, if you keep it as epsilon, even it's easier. You will see after a while. So I'm telling you, epsilon is nothing but a value which approaching 0. And keep it as an epsilon. Let us proceed. When I proceed with the table, the other items are having no problem, but epsilon will appear with me here, and epsilon will appear with me here, and that's it. Now we will evaluate or we will interpret the system. How to interpret the system? Interpret, we said we want to look at the sign of the first column. The first column sign, we need to check it, whether there is changes in sign or not. The problem for 1 and the 2, they are okay, no problem. But epsilon is a value which I assume. So what should I put its assumption, positive or negative? He said put it as you like, positive or negative. And the proof is shown here. If you put epsilon as a positive quantity, nothing will happen. You are going to get these signs, positive, 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 negative, positive, positive. If you put epsilon negative quantity, it's going to come here. So the sign is going to be positive, positive, then negative, then positive, positive, positive. Compare the two results obtained. Compare this sign and this sign. You are going to find that the number of changes in sign here are 2. 1, 2. And the number of changes in the sign here is going to be 1 and 2. So whether you are putting epsilon positive or negative, you are going to get the same changes in sign. So it's going to cause no problem, no effect. For a matter of simplicity, always assume it's positive. Always assume positive. But actually, it's no problem to make it positive or negative. Before we go to the next slide, if I want to interpret this one, how can I interpret it? Of course, we agreed that this value is positive. This is positive. This is positive. Now I will put this is positive. So when I look at this one, how this become negative? Any epsilon here, value of epsilon, we are going to assume it's 0. So this is something like 0. 6 epsilon is equal to 0. Something like this. Epsilon in the denominator is considered as very small quantity with positive sign, as I agree. So what is the result? The result will be negative sign. See how? So that's how we can interpret it. Whenever we have 6 epsilon, whatever kind of value multiplied into epsilon, replace it by 0. But when we have epsilon by itself in the denominator, as you see here, you assume it's very small value and consider the sign. So the sign here will be positive. So we have minus 7 divided by positive something, whatever that value. The result will be negative. Let us come to this one. When I want to evaluate this one, 42 epsilon means 0, minus 49. 42, 6 epsilon squared, that means 0, nothing. 12 epsilon means 0. What is the remaining is minus 49 divided by minus 14, which equal to positive quantity. And when you continue, you are going to get here positive quantity. That's how we got the values or the sign for the first column. So again, if I want to interpret this one, the interpretation, we have one change in sign from positive to negative, then from negative to positive. That means there are two changes in sign. That means there are two poles on the right hand side, which indication that the system is not stable. Another way to deal with the previous example, another way is called reverse coefficient method. So if there is a 0 in the first column, you can do it by reverse coefficient method. What is the reverse coefficient method? We are going to distribute the coefficient of the characteristic equation in reverse way. What is the meaning of reverse way? I will start from the end to the beginning. So notice 3, this 3, then 5, then 6, then 3, then 2, then 1. So we are going to put the coefficient in reverse way and calculate. You are going to get the same result. I mean, calculate, you will not find 0. 0 is not going to appear, but you will have the same changes in sign. Here, positive to negative and negative to positive. So two changes in sign, which indication of two poles on right hand plane, which means the system is unstable. The other special case is when we are having a row of zeros. That means when we calculate the table, you will find that there is a full row of zeros. Something like this is the table. This is the table. While calculating, I will find like this is 0, 0, 0, 0. So full row of 0. This is giving me certain indication. It gives me the indication of even polynomial. Even polynomial means we are having whatever pole located on the upper side is going to be met with a pole on the lower side. So when it's even polynomial, that means we are having pole here. There must be another pole here. If there is a pole at this point, there must be another pole at this point. If there is a pole at this point, there must be a pole on this point. That's what we mean by even polynomial. And when it comes to even polynomial, there is a chance to get the poles on the j omega axis. So the pole will be located at j omega axis only during this time when there is a row of zeros. Now, how to deal with this case, how to build the table, I'm going to explain it. But now I want you to know what is the meaning of even polynomial. Even polynomial means that there are a pole in the upper side same as the pole on the lower side. I mean, it's mirror image. The upper side is mirror image of the lower side. So whatever you see here, if I tell you that there is a pole here, that means there must be another pole here, and so on. Now, how am I going to deal with the system if there is a row of 0? Let us get this example. In this example, we find that the characteristic equation s to the power 5 is fifth order. So s to the power 5, 4, 3, 2, 1 until 0. We are going to distribute the coefficient 1, 7, 1, 7, 6, 42, 8, 60, 56. Notice that we can divide this row by 7 to get simpler values. This step is optional. It's optional. You can do it or you can avoid doing it. It's up to you. But if you divide the row by 7, you will find here 1 and 6, 8, easier value to deal with. That's the only reason for putting this. Okay, now when we divide the row by 7, you will get here 1, 6, and 8. Let us continue. When I continue the table, we will get here 0, 0, 0. This is telling me that we have row of zeros. The whole row is zeros. So if the row of zeros, how can I continue? I will come to the point of continue. How to continue? I will come to the point. But what I want you to know that we are having even polynomial now. Even polynomial will come in here in this side. There is even polynomial, which telling me that there is a chance of poles located at j omega axis. Now, how am I going to deal with this row of zeros? That's going to be explained in the next slide. Once I get the value for 12 and 0, as I mentioned in the next slide, as shown after a while, you will continue the table to get the rest of the item. Then we will start the interpretation after this of this table. But when we have even polynomial, the interpretation will be a little bit different. Let us first of all solve the problem of row of zeros. Now let us remove the row of zeros, or find solution for the row of zeros. It's not removal, but it's find solution for the row of zeros. To solve it, the method is saying we are going to get auxiliary polynomial. This is the auxiliary polynomial. Where is it created from? It's created from the row before the row of zeros. Like if you notice here, this is the row of 0. This is the row of 0. From the row before to this row, that means s to the power 4 row, we are going to build this polynomial. What is the meaning of building this polynomial? Notice that this is 1 s to the power 3, s to the power 4. And this is 6 s to the power 2, not 3. Keep in your mind, because this row is taken originally is taken from s to the power 4, s to the power 2, s to the power 0. So when we want to build the polynomial, it's going to be 1 s to the power 4 plus 6 s to the power 2 plus 8 s to the power 0, or 8. So this polynomial, we will take it and we will differentiate it with respect to s. So the derivative of it, dps by ds, is equal to 4s to the power 3 plus 12s plus 0. Take the coefficient of each s and replace the row of zeros by it. That means this 0 will be removed and we will put 4. This 0 will be removed and we will put 12. This 0 will be removed and we will put 0. Now we get from the row 4, 12, and then 0. We can divide it by 4. So if I divide the row by 4, this will become 1. As you see here, this is 1, this is a 3, and this is 0. So that's how we can solve the problem of the row of zeros. Now the row of zeros become 1, 3, and 0, which normal. Now we can deal with it. What is the remaining part out of this process is to keep in our mind that this is a function with even polynomial, which going to be the even polynomial start from this row till the end is considered as an even. The rest is not even. So in the way of analysis, or in the way of interpretation, we are going to find that this is to be interpreted such that we have possibilities for left hand side, right hand side, and j omega, and the other only left or right. So let us now look at this example. With this example, we have the characteristic equation, and from the characteristic equation, we will build the table of Rourth-Hrwits table. So building the Rourth-Hrwits table, we come across this row, which 0, 0, 0, and we are going to solve it. To solve it, we are going to build the auxiliary polynomial, which to be taken from the previous row. So from this row, I'm going to take s to the power 4 plus 3s squared plus 2 equal to 0, or sorry, dp by sorry, this is dp, or sorry, p is equal to this value. So now if I want to differentiate it, dp by ds is to be calculated as 4s plus 6, 4s to the power 3 plus 6s, and that's it. So we will take this 4 and we will put it here. This 6 we will put it here and finish. The remaining are zeros. So divide the row by 2, it will become 2 here and 3 here. That's how we can deal with it, and we will continue till the end. Now, after we finish this step, we are going to interpret the table. The interpretation here, as I said, there is even and not even. Let us look at it. This is the row of zeros. We have to keep it in our mind. This one is the row of zeros. The even polynomial will start from the row before it till the end. So from here till the end, we call it even. This is not even. That's how we can differentiate. So we will start the interpretation from even. Even is s to the power 4. That means we are having 4 poles in this system. 4 poles. If it's s to the power 4, that means 4 poles. Where is their location? Here we are going to check the change in sign. Any change of sign here, there is no change in sign. That means there is 0 pole on the right hand side. Right hand side will be 0. Then in even polynomial, because it's even, and as I mentioned earlier, the upper side is mirror image of the lower side, and this story, if there is no right hand side, that means there is no left hand side. No right hand side means no left hand side. That means the left hand side will be 0. Usually in even polynomial, right hand side equal to the left hand side. But we are having 4 poles here. Where to put them? They are going to go to j omega axis. That's for the even. How about the not even? Not even, we will check the number of changes in sign. This is positive, positive, negative. This is one change. Negative to positive, another change. So there are 2 changes in sign. That means there are 2 poles on the right hand side. 2 poles on the right hand side. And how many poles are there? There are 4. Why? Because the total is 8. 4 even, that means 4 not even. The 4 even, we know them. All of them goes to the j omega. The not even, 2 will go to the right and 2 will go to the left. Remember, in the not even, it's not necessarily to get them equal. Sometimes they are not equal, the right and the left. Only in even they must be equal. Let's see the interpretation in the next table, in the next slide. So whatever I mentioned in the previous slide is discussed here. The detail is shown here. Here he's showing how he interprets the even polynomial, and here he interprets the not even polynomial. In the expression of the result here, we are going to express the result like this. Later, you will find that we are putting them on table. We will say even, not even. Then we are going to say something like this: right hand plan, left hand plan, and j omega. So in the even polynomial, right hand plan is 0. That means left hand plan is 0, which means all the poles will go to j omega. In the not even, we found that there are 2 poles on the right. That means the remaining will go to the left. Usually in the not even polynomial, there is no j omega, no j omega, no j omega. So whatever poles available will be distributed between the right and the left, not equally, not necessarily to be equally. Here it comes equal by chance. So sometimes they are not equal, sometimes they are equal. Let us look at this example. In this example, he said find the number of poles on the right hand plan, left hand plan, and the j omega axis of the following system below. So this is the system. We will calculate the characteristic equation. This is the characteristic equation, and we will start the calculation. While calculating, I will find that there is no 0 on the left. I mean, no special case. No special case. No zeros in the first column. No 0 available here. And no row of zeros. Row of zeros is not available. That means we are going to do it with the simple style, simple way. So we will distribute the coefficient, simplify if there is a simplification. Then we will calculate for interpretation. You will find the number of changes in sign. Positive to positive, positive to positive, positive to negative. This is the first change. And then negative to positive, which is the second change. So there are 2 changes in sign. 2 changes in sign means on the right hand plan there are 2 poles. So I can say right hand plan, left hand plan, j omega. Actually, j omega is not needed here because we don't have even polynomial. So even this one is not needed because no even polynomial. Here we will have only even because what we have is only even. Even no need to write. So in the right we have one. The total are 4. Total are 4. 2 goes to the right. 2 goes to the right. That means the other 2 will be to the left. Again, remember, they are not equal. I mean, not necessarily to be equal. They can be equal or cannot be equal. Sorry, they can be equal and they can be not equal. This is the interpretation. For this system, same style, we are having a transfer function. We will calculate the characteristic equation and we will build the Rourth table. Let us see the Rourth table in the next slide. Here is the table. When we calculate, we found that there is a 0. So if there is a 0, we will replace it by epsilon and we will continue. Now it's the time for interpretation. Remember, there is no row of zeros. That means there is no even polynomial. So the pole is going to go left and right only left and right. So if I want to put the sign here, that's going to be positive here, positive here. This is epsilon, I will consider it's positive. Now how about this one? How to interpret this one? Remember, 3 epsilon is going to be 0, nothing. The sign here is, epsilon is positive in sign. So let us say it's positive 0.1, for example. So that's result on the sign is negative. This is 0. This is 0 and this is 0. The remaining is minus 16 over minus 12, which means positive. And the 1 is positive. So there are 2 changes in sign and the number of poles are 5. That means there are right hand plan, left hand plan. That's what I have only. There is no j omega. No even and not even. All not even. That means we are going to have 2 in the right and 3 in the left. Notice they are not equal, not necessarily to be equal. They are equal only in the even polynomial. For this one, the same style. We are having open loop transfer function. We will calculate the closed loop transfer function and we will distribute the coefficients. As you see, we notice that there is a row of 0 here. So we will do the interpretation. In the interpretation, let me do the interpretation here. Once we have row of zeros, that means we will have left, right, and j omega. Left hand side, right hand side, or left hand plan, right hand plan, and j omega. So how to interpret them? We are going to consider the row of zeros is this one. That means the even polynomial will start from here till the end. How many poles in the even polynomial? There are 6 because this is 6th order. So 6 poles located at this side. And the total are 8. That means 2 poles located here. So in the evaluation, we will check in the even polynomial first. In the even polynomial, we found the number of changes in sign here, nothing. I mean positive, 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 negative. That means this is one change in sign. Positive, then negative, then another change in sign. After that, no changes. That means we have 2 changes in sign, which telling me that j omega, there are 2 poles. Right, not j omega. Right hand plan, there are 2 poles. Which means, guys, blindly, left hand plan equal to 2. I'm talking about only the even polynomial. 2 right, 2 left, but the total is 5. That means the total is 6. Total is 6 means there are 2 remaining. Where are they going to go? Those 2 are going to go to j omega. So, and j omega will be 2. 2 poles will go to j omega. That's in the even polynomial. How about not even polynomial? In the not even polynomial, there is no changes in sign. That means no right hand plan, which means the 2 poles are going to go to the left hand plan. So this one in this side, here, and this side, we are going to find that there are 2 poles on the left hand plan equal to 2. Let's see the answer in the next slide. Here is the answer. Here is showing the detail how to replace the row of zeros by the other coefficients. And finally, this is the answer. In the even polynomial, there are 6 poles. 2 goes to the right means there are 2 goes to the left. Automatically, they are equal. The remaining out of 6, the remaining will be 2. They are going to go to j omega. In the not even or the rest, we are going to find that there is nothing going to right hand plan. That means they are going to go to the left hand plan. J omega is not applicable here. There is no j omega. Here he put the total. 2 plus 0 equal to 2. 2 plus 2 equal to 4, 2 plus 0 equal to 2. Here we will use Rourth-Hrwits for design for stability, like what you can see here in this example. If I want to design, that means there must be a constant k, which will help us in our design. Of course, here he's saying find the range of k for the system that will cause the system to be stable. That means what is the range of k for stable, range of k not stable, and range of k for unstable, marginally stable. We will understand what does it mean after this. K always more than 0. K cannot be less than 0. You always consider that K more than 0. Okay, in the answer, we are going to calculate the closed loop transfer function. So the closed loop transfer function will be seen in the next slide. When we get the closed loop transfer function of the system given earlier, you will find that the characteristic equation is as you see here, and K will appear in the denominator of the characteristic equation. Distributed on route table, you are going to find K appearing in this element and this element. Now let us check how to get the value of K for stable, marginally stable, or unstable. Notice it's clearly shown here that as long as K smaller than this value, the sign of this member or this item will be positive. And if this is positive, that means we are going to have no changes in sign. That means the system will be stable. So for the system to be stable, we must get the value of K from 0 to less than 1386. Finish. Now, what about marginally stable? Or what about unstable? First of all, unstable if the value of K greater than 1386. Greater than 1386, we are going to get negative here, so the system is unstable. How about if K equal to 1386? If K equal to 1386, that means we will get 0 here. 0 means row of zeros, as you see, which means we are going to get the system to be marginally stable. Marginally stable means there will be oscillation and the frequency and this story. So if I want to get the frequency of oscillation, what am I going to do? We are going to build the auxiliary polynomial from here. If it's needed for whatever reason, we can put it here, but it's not needed. I just want to get the auxiliary polynomial from here. See what we are going to do with it in the next slide. The auxiliary polynomial is what you can see here. When you use this equation to calculate the value of S, you are going to find that S equal to plus minus J 8.775. 8.775. That's when you calculate S from this part. How this can help me? This can help me to know what is omega, what is the frequency of oscillation. Because we know in general that S is equal to J omega. And this value, the value of S is J 8.7. That means this 8.7 by itself is going to be omega, which having a unit of radian per second, which is the frequency of oscillation during the marginal stable. That's all about stability. I hope it's clear. Thank you very much.